What's the two categories of electrical? What is a motor? So we have what we call a rotary actuator, and then we have what we call a motor. Do y'all know the difference? What does the term stroke mean? When we use the term stroke, we're talking about how far an actuator can move something. So it's pretty obvious on a cylinder what stroke it will be, and that would be something that you would order, right? Is not only how much force you got to generate, which would determine the size of the piston, but how far do you need to move it, which would be the what? Would be the stroke. So a rotary actuator rotates in an arc, but it has a limited stroke.
A what?
A limited stroke. So it can only rotate so far. Okay, y'all understand?
Why?
Because of the mechanics of the thing. So your steering wheel's got a limited stroke, right? Why? The wheels are only going to turn so far. So if I had something turning my steering wheel for me, which obviously we're going to have that, it would probably be some type of actuator that had a limited stroke, right? You understand that? So it's limited by the mechanics of the thing. When we was looking at actuators, I realized that all we talked about was actually linear actuators, cylinders. When actuality, when we go over there and look at the thing, we got several, especially on the Festool line, we have a rotary, literally a rotary actuator. So this is limited by the mechanics of the device itself. So I could have a motor. So a motor is an actuator that basically has no internal limited stroke, which means it can do what? Keep rotating, rotating, rotating. We can limit the stroke, but we do it outside of the motor. What do we use to open? If you've got electric locks on your car, what do they use? Do they use a solenoid or do they use a motor? They use a motor because the solenoid would let you unlock it, but what you couldn't do. You couldn't lock it unless they come up with some method. So it's a motor in there. It's a locked motor, but it doesn't have a limited stroke, so we limit the stroke outside of it, right? You understand? So there's some type of switch that when the thing unlocks, it cuts the motor off. And don't let it do what? Come up again until you do what? Take it back down. Does that make sense? So I'm not saying that a motor cannot have a limited stroke, but it's got to be limited outside of the motor. Rotary actuators, they are limited internal, right? You understand that? So these are the kind of like the rotary actuators. If this is going to work. Huh. So now you should be able to see the animations, right? So all we're doing on this one, the internal works of this one limits the stroke. Here, of course, when the piston hits one side, it limits the stroke. And you'll see both of these out there. And these we call rotary actuators. And of course, these are just manual or solenoid operating directly. And then I got a handout, guys, that's going to give you all these symbols because symbols are very important in our trade, right? I gave a test to my solid state class, and I was kind of discouraged on that. So electric motors. So a motor, huh?
I just have one question. Are all rotary actuators limited?
A rotary actuator rotates in an arc and has a limited stroke. So would that mean all? Okay. A motor rotates in arcs, but it has what? Unlimited. It has no stroke. It'll run forever. So it goes a lot, a rotary actuator might go more than 360 degrees, but eventually it's going to hit an end stop and it's going to do what? Stop. So a rotary actuator, the stroke is limited mechanically, right? You understand that, by whatever we're running it with. An electric motor has no limited, has an unlimited stroke. So we need to understand a little bit about number systems. So has anybody been introduced to binary? Huh? Yes? Okay. So y'all know what's the advantage of binary? Well, you can't really say that because any numbering system could technically have a limited number of combinations. A binary is very inefficient. I mean, binary is very inefficient because each digit only has 2 combinations. So that means if I'm going to represent really big numbers, I'm going to have extremely big numbers, right? You understand that? Because you only have 2 combinations. A decimal, each digit can have 10 combinations, which means if each digit can have 10 combinations, it means we can represent larger numbers with a fewer number of digits, right? You understand? Actually, hexadecimal is more efficient than binary. Because the hexadecimal, we have 16 combinations. So now we can represent extremely big numbers with very few digits, right? You understand that? Yeah, 16 digits of hexadecimal would blow, hexadecimal would blow decimal away. But 16 digits of binary, we can only represent 65,530, a number of 65,535 with 16 digits, right? You understand that? This is the advantage of binary right here. We can do what with it? We can store it. We can send it real easy. And computers can do what? Process it. The circuits that process the information are very, very simple. Try to come up with a circuit that adds decimal numbers. It would basically be impossible. But we can have circuits, very simple circuits that add binary numbers. Very simple. So the circuit to add, I'm trying to find my drawing thing because it's right on top of this. So this is a binary adder. We come up here, go through an exclusive OR, and then we come over here. That would add them, and then I come up here and I take care of my carry, and that's an adder. That's an adder for binary, 2 binary bits. That's all there is to it. So if I tried to add decimal numbers, basically there's no way in the world I could design a circuit that would add decimal numbers. Because now I've got to be able to represent those 10 combinations. I've got to electrically represent those 10 combinations. So what that meant is I would have to use 10 different voltage levels, right? 0 through 9. So let's say this would be 0. Then I'd use 1 volt to represent a 1, 2 volts to represent a 2, 3 volts to represent a 3, 4 volts. You understand that? So now I've got to have a circuit that detects when it's 2 volts, when it's 3 volts, right? You understand that? Very complicated circuit. A binary, we can use just 2 voltage levels, right? I could use like 0 volts to represent what we call a 1, and I could use some voltage to represent a 0. So I could use 0 volts to represent a 0, and some voltage to represent a 1. So all our PLCs use 0 volts to represent a 0 outside and uses plus 24 volts to represent a 1. So now I'm either putting a 0 there or a 1, right? You understand? We bring that into a computer. We can add them, we can subtract them, we can multiply them, we can divide them, right? You understand that? The circuits that do it would be extremely easy. So this is the big advantage right here. We can process binary with a what? With a computer. Because computers are digital. So all this guy literally sees, everything it does is nothing but ones and zeros. Everything you see on this screen is done with nothing but ones and zeros. Everything I store is in ones and zeros. Everything I transmit is in what? Ones and zeros. So that's a big advantage of binary. It's not good for us because why? So what numbering system do you learn your whole life? Yeah. So, if I came over here and I wrote down, 1,683, you would know the weight of that number. If I came over here and did this, you have no idea what the weight of that number is because we don't understand the binary numbering system, right? So we have to punch this into a calculator or we have to learn how to convert it. So when we use the term digital, we're talking about, and of course, we gotta represent this two different ways. We can either represent it with current. So we have a method called current loop, which is the way we transmit it, or we could represent it with a what? Which is voltage, and which is the most popular to represent digital information? Voltage, yeah, we use voltage. So what type of motors, electrical motors, do we have? We have two categories of electrical motors. What are those? No. That's a type of a motor inside a category. What's the two types of categories of motors we have? What? AC and DC. So the motors are either going to be AC motors or DC motors. So we gotta have some type of advantage over one of these to decide which one we use, right? You understand? So what advantage does AC motors have over DC motors? Cheaper. AC motors, we can run AC motors off induction, which means, so all electrical motors, how do they work? Magnetically, yeah. So they work on the attraction or the repulsion of magnetic fields. Okay, y'all understand that? Well, what's nice about AC is, so I've got a device on an AC motor that we call a rotor. And there's no electrical connection to it. Because the way it works off, and then I have these windings out here, and electricity, we call these the stator. So that's the stationary field and the rotating field, right? You understand? So it's no problem as far as me generating an electromagnetic field here, right? So what do we need to generate an electromagnetic field? Huh? Well, we gotta have a conductor, right? And then all we have to do is put current through the conductor. That's all we need. So if I put current through a conductor, it generates a magnetic field. Okay, y'all understand that? And we call these electromagnets. So what advantages electromagnets have over permanent magnets? We can control it, right? We can turn it off or on, right? And then we can also control the string. So what we do on an electromagnet is we have all these little magnets, and then what we do is we start winding the conductors, and then every time we wind them, the magnetic field produced in one combines with the magnetic field produced in the other. So the more windings we have, the stronger the electromagnetic magnet becomes, right? They'll follow this. That makes sense. And then, of course, we need to wind it. If we wind it around a metal, then metals concentrate magnetic fields. So what we'll have is we'll have up here on this stator, the way I got it drawn, and unfortunately all our magnets are over, all our big motors are over on the motor control labs. So we have these. We'll come down here and I'll draw it like this. We'll have what they call a stator pole. And then it'll come up. And then the wires are actually wrapped around here. So if I come over here and I I come over here and I put current through this guy, it's going to generate a south pole. Well, on AC, what's going to happen? Now, we'll do this with DC, but we got to do something a little different with DC. What's required to induce a voltage into a conductor magnetically? What do we need? So we got what we call inductions. How do transformers work? It induces a voltage from one set of windings into another set of windings, and it does it magnetically, right? You understand that? So to induce a voltage magnetically or an electromotive force, first of all, we got to have a what? We got to have a magnetic field. And what's the second thing we need? Yeah, we need a conductor. And then what's the third thing we need? A relative motion. And what do we mean by relative motion? Either the magnetic field has to cut across the conductor, right, you understand, or the conductor has to be moved through the magnetic field. And either one of those, we get an electromotive force. Now, DC does this, but DC only does it once. When you first turn something on, then you might get motion, right? You understand? But the problem with DC is it comes up there and it just sits there, right? You understand that? What does AC do? It constantly changes what? Polarity. So it means if I did AC, what would happen is I would come up here and I would build up a magnetic field. It would expand out, and then then it would drop down to zero, and then it would expand out, going in the opposite direction, right? You understand that? So what determines the amount that we get? Let's go 1, 2, 3. We're talking about EMF. We're not talking about current. We're going 1, 2, 3. So over here I put magnetic field first. So what in relation to the magnetic field determines how much EMF you get? The strength of the field. Okay, so the stronger the field is, the more EMF we would induce into that conductor when it moves through the field or the field moves across the conductor. What about the conductor determines how much EMF we get? The number of loops. So what happens is every time we do this, I induce a little one little thing like that into one of the windings. And then if we wind the windings in the same direction, then we basically, these little old EMFs that we're generating are in series adding. And what happens? It causes the EMF to go up. And then what's number 4? The speed of the motion. And that's the way we say, this is why we get AC when we spin a conductor through that, is that your magnetic lines of force are moving like this. So what happens when your wire's out here, when your thing is running perpendicular to the wire, and we use a railroad track. So if I was walking down the railroad track like this, I wouldn't be crossing the track, right? You understand? And then what we do is we start slanting just a little bit, so eventually what would happen is I would eventually cross the track. And of course, if I went like this, then I would get maximum speed, right? You understand? So this is why when we induce AC, we end up with this waveform like that, which we call a sine wave. But what's important to know is that AC automatically generates what? Motion. So that means if I had a bunch of conductors over here in my stator, in my rotor, when I put AC on this thing, it would come flying out and it would induce a current into those things, right? You understand that? If it induces a current into that thing, then what's it going to do? It's going to create a magnetic field. Here, if it's going out here, it's going to cut into that one. And so if this was a north, then what's it going to do from there? It's going to induce the south, right? You understand that? And so we call these AC motors induction motors because you get energy into the rotor through induction. So we have no electrical connection between the rotor and the stator because the current in the rotor is induced in there. So that means, we call these squirrel cage rotors. So the conductors are actually shorted out on the end. They're in a slight angle to cause the thing. So this actually here would be the conductors. So what happens is when I start it off, this is going to be basically like a short circuit, guys, and it's going to induce a lot of voltage into the rotor, right? You understand? Which is going to cause a lot of current to flow. We have a real strong rotor current. We have a strong stator current. So these motors create a lot of torque when you do what? When you start them. But as it comes up, then the speed of the rotating field and the speed of the rotor start matching each other, which means what's happening, even though I'm not changing the speed of the 60 hertz, what's happening is how much voltage or how much current we get is a relationship between the speed of the rotor and what we apply to it. So as the speed of the rotor comes up, you have the difference in frequency goes down and you induce less voltage into the rotor, which causes to create less torque. But when do you need the most torque out of a motor? When you start it. So whether you understand that precisely, you'll learn more about it, especially if you take the motors class. But this is why AC motors are so cheap, because the rotor itself is nothing but a big chunk of metal and big solid conductors running through there, right? You understand that? A DC motor, how do you create a magnetic field, electromagnetic field in that rotor? Well, you got to take it in there, right? You understand? So the way a DC motor works is we have a unit out here. So a DC motor, we have to have brushes. Now the field can either be a permanent magnet, but at least one of the fields of an electrical motor has got to be an electromagnet. So what would happen if I came over here and put DC into this thing, then what would happen is this guy would come up and it would just stop when it lines up, right? You understand? Unless we do what? Unless we switch the magnetic fields. So what's happening with a DC motor, it's got this unit back here that we refer to as a commutator. Can y'all see that? Commutator, a slotted copper ring used to transfer current from the source to the armature. The slots mechanically change the direction of the current flow in the armature, causing the motor to do what? To rotate. So what happens is right here where the magnetic field is, and I know this is not being recorded, is I switch that sucker right here. So if this is a south, and I come over here and it gets right there, if I switch it from a north, then what's it going to do? It's going to make it swing to the what? To the south, and it's going to cause it to rotate. So what happens on a DC motor is the rotor has got to be wound. It's got to be an electromagnet. So if it's got to be an electromagnet, it means it's going to take a lot of copper in there, right? And then we got this mechanical thing that's doing the what? That's doing the switching for us, right? And I'll pass this around. So this is a DC motor. So this is the DC motor, and I like this because you can actually look at it. So there's the brush right there. And then when you rotate it and you spin the thing with your finger, you can actually see the commutator actually make the switch. It's going to be hard to see right here. I don't know if y'all can see the little black line switching there. So what's happening is that when this thing spins, it constantly switches the magnetic field on the rotor, right? You understand, which causes the motor to rotate. So the problem with DC motors is they're a lot more expensive. This is a permanent magnet DC motor. We do have different, if we leave the field alone, then what would happen is that, and we'll talk about that in a minute. Here we go. So this is a DC motor. And what I like about this one is you can literally see the brushes. So what do we have to do with this? Well, eventually the brushes are going to wear out, right? You understand? And eventually the commutator is going to get full of gunk. So what you have to do on the DC motors, you have to have a preventive maintenance schedule, because you don't want the mounting assembly that's got the wire coming into it. So it's got this thing that comes out here. It's got a little mounting assembly in here. If that ever gets into your commutator, it'll tear it up. So you got to monitor those brushes, right? You understand? You got to change those brushes out. And then you got to clean the commutator. So the commutator's got to stay nice and clean. So a motor, if you don't do the preventive maintenance on a DC motor, eventually it's going to do what? It's going to wear out. And you're going to cost a lot of money. These DC motors cost a lot of money per horsepower. So the advantage of AC motor is cheaper. DC motors, basically we can control them a lot better. So DC motors are real easy to control. So if I reduce the amount of current I put into the armature, the motor slows down. If I increase the amount of current I put into the armature, the motor speeds up. Right? Does that make sense? So these guys are real easy to control. So all the motors we have on our manufacturing line over there are DC motors. And we'll talk about how, and it's controlling the speed and controlling the torque. I'm going the wrong way. So these are the types of DC motors we have. We have shunt series and compound DC motors. We have stepper motors, and we have what we call brushless motors. I don't think we got any brushless motors on any of our line over there. Over here on the AC, you have single-phase motors, you have three-phase motors, and you have what we call synchronous motors. So all the AC motors in your house are single-phase motors. Three-phase motors, we have delta. So single-phase, we have capacitive start, we have capacitive run, we have split phase, and shaded pole. Three-phase, we have Y delta, and wound rotor motors, and then we have synchronous AC motors. Okay? So this is DC motors. By the way, a lot of people call the rotating part of a DC motor, they call it the rotor, but technically it's called the armature. So the outside field is called a field. This could be a permanent magnet or could be an electromagnet. Permanent magnets are going to be your really, really low torque motors, your real little tiny horsepower motors. So your starter motor on your car does not use a permanent magnet. But the ones that run your windshield wipers, the one that runs those are probably permanent magnet motors. The one that runs your locks. So the field can either be an electromagnet or a permanent magnet. And, sometimes they call this a stator, but technically it is what we call the field. The rotating part of a DC motor, we refer to it as a what? It's the armature. That's the technical name. But some people refer to it as the stator, which is what we call it an AC motor. The commutator, this is a slotted copper ring used to transfer current from the source to the armature. The slots mechanically change the direction of the current in the armature, causing the motor to rotate in a certain direction. So if we change the polarity going to the armature, the motor will reverse. So we're very easy to reverse. Brushes, these are common carbon blocks with copper wires attached using the transfer current from the power source to the commutator. Normally reversed by changing the polarity applied to the armature. We okay? Any questions here? So what's the problem with DC motors? What's the cons of DC motors? They cost more per horsepower, right? So when we talk about motors, we talk about the over here we rate them in horsepower. Everybody else, they rate them in what they call kilowatts. How much power do they need? The problem with the horsepower is that this is, of course, was developed in the United States. And what they were trying to do was, up until this time, what we were doing is we were running things with horses, right? You understand? So what they was trying to do was to come up with a method where people that used horses, so they knew how much power horses could generate, how much power, so they understood that, but they didn't understand motors, right? You understand? So they came out there and they got a bunch of horses and they pulled them and they pulled a certain weight over a certain distance and they averaged that together. And then they did this exact same thing with a steam engine, right? And then now they can say, okay, if this is 5 horsepower, right, you understand, a 5 horsepower steam engine, then they say, well, 5 horses could pull the same thing, over a load over a certain distance. The problem is, what does that mean to me when I pay my power bill? It don't mean anything. So we came up with a relationship between horsepower and electrical motors. And a rule of thumb, guys, and it's not 100% efficient, but it works out good enough for calculations, is 746 watts of power per horsepower. Power. So now, if I wanted to figure out how much current a motor would draw, I would have to take the size of the motor in horsepower, multiply it by 746, and then divide that by something. Europe got away, everybody else got rid of that a long time ago. So they rate motors in kilowatts. So I've got a 10 kilowatt motor, then I know it's going to need 10 kilowatts worth of power. We're still dealing with what over here? Horsepower. So this is a type of motor called a shunt motor. And notice here we use 2 electromagnets. We use the field as an electromagnet and the armature. So this is the symbol of an armature of a DC motor. So if you ever see this thing, this circle with these 2 little blocks on the side representing the brushes, this means that's the armature of a DC motor. That makes sense? Now, what would be the advantage of this guy? Well, what happens is that the amount of torque the motor generates is how much current you have in the armature, or the strength of the armature field repelling or attracting the strength of the other field. That makes sense. So a permanent magnet, you're controlling one field. You're not controlling the field. You're controlling the strength of the armature field, right? You understand? With a shunt motor, we can control both of them. So the more current I put in the shunt field, the more starting torque and run torque the motor will have. So with these separately excited fields, then we can control not only the speed, we can also control the torque. Now what's so funny is that we can control the speed of the armature by changing the amount of current. Now, how do we change the amount of current? Well, the armature is going to have a certain R. And what's so strange is that, and we're not going to explain why, but as the motor comes up to speed, the R of the armature goes up. Huh? The resistance does. It works on something called counter EMF. So what happens is that when this thing here spins, it's got a bunch of copper wires in there, right? You understand? This is the magnetic field. So if this armature is spinning, it's going to induce a voltage into the armature. Now, the voltage that it induces into the armature is opposite of the applied voltage. So what happens is, the faster the motor runs, the less current the armature draws because of the counter EMF. And what happens, and that's what you want. So when the thing is setting still, you have no counter EMF, so you get the full strength of the field and you create a bunch of starting torque, right? You understand? But as the armature comes up to speed, that induced voltage from the stator subtracts from the voltage being applied to the armature and causes the motor to produce less torque. And it runs at a speed that generates enough torque to run the load. So most people say the R of the armature goes up, and that's true, but it's doing it electrically, right? You understand? So it's doing it through what we call counter EMF. So what happens is this guy here's got a certain R. So what happens, depending on the voltage I put across that thing, if I put more voltage, it's going to produce more current, which is going to cause the motor to run faster. If I put less voltage on the armature, the motor's going to run slower. Now the problem with the field is that the more voltage I put across the field, the stronger it gets, the more counter EMF it induces, so the motor runs slower. So what's so strange about a DC motor is that the motor will run a speed proportional to the applied voltage on the armature, and it's inversely proportional on the stator. Not the stator, guys, I said that wrong. On the stationary field.
Do you refer to it as stator?
No, I refer to it as the field and armature. But what happens is that when they came out with AC motors, they started calling it the stator and the rotor. So what's happened over time is a lot of people will refer to these as and it makes sense. The stationary field, right? So we always got to have a stationary field, and then we got to have a what? A rotating field. And then those guys, somehow we gotta switch them, right? You understand? What's nice about AC, it automatically switches the field. DC don't do that. So what do we have to do on a DC motor? We gotta switch it with a what? With this thing called a commutator. So we let the motor itself switch the field. Y'all understand that? So the rotor itself constantly switches the field. And if it switches the field, then it's always going to be doing what? Attracting and repelling. If I didn't do that, the motor would come up and line up and just do what? Stop, right? But what we're doing is it comes up and lines up, and as soon as it lines up, what do? They change the field. Now it's not lined up anymore, so what does it do? It spins until it gets to the other side. And when it spins and gets to the other side, what do? Swap the field. But they let the motor itself do that for us. So I could set up here with a switch on a DC motor, right, you understand, and every time it stopped, I could flip the switch and change the field, and it would spin around and stop again, right, you understand. And if I could get in sync, then of course I could make it spin, but that's going to be highly unlikely. So this commutator automatically does what to the DC motor? It automatically switches it for us. But the problem is, as soon as it does that, it means I've got to do what? I got to have brushes, right, you understand. And then, of course, I got to keep the commutator clean. We got one over there in the motor controls lab. If y'all take motor controls, whoever teaches that should show you that motor where they did know. What they did is they took off the covers off the brushes. And then what does guys do? They just left them off. And that motor is just tore to pieces because what happened is now it got gunk in there and got it on the commutator. Causes the brushes to get soft up. Now it's got oil on your brushes, right? So now being real hard, they become soft. They wear out. As soon as they wear out, they get into the commutator and tear the commutator apart. And now what can you do? Huh? Go out and buy a new one, right? So yeah, you get that, you tear up that commutator, you got really big problems. So what you have to do on this is you have to have some type of preventive maintenance schedule where you go out and do what? Just like in robots, you should have a preventive maintenance schedule where you go out and change those batteries, right? So this is called a shunt motor. What's nice about a shunt motor, it tries to maintain a constant speed. So what they call these constant speed motors. Because if the voltage goes down, this guy would try to slow down. If the counter EMF goes down, which would cause the motor to go back up. So this is a nice thing about a shunt motor. You get a lot of starting torque, right? You understand that. But these guys are often called constant speed motors because they try, but they're over a certain range. Whether you understand it, that's okay. All you need to know is a shunt motor usually tries to run at a good speed, right? Everybody understand that? Good speed regulation over varying voltages, and it has okay starting torque. This is a permanent magnet motor. This is what all ours are. Used on both the Omnitrol Tesla manufacturing line. Speed changes with armature voltage, which is going to change the what? Yeah, so if I change the voltage to a resistance, it's going to change the current, right? Good speed characteristics, good starting torque, used in very, very low horsepower applications. So we've got little old tiny motors over there. These guys are cheaper because we don't have the windings out here on the field, right? You understand? So the motor I passed around was a permanent magnet motor. This is, I left that one. This is a series motor. Now what happens here is that when we start this thing up, that series field is very few windings because it's in series. Your rotor is sitting here not turning, or the armature is not turning, so it almost has zero resistance, right? The only thing it's got is the resistance of the wire. So what happens is you start out with an extremely strong field and an extremely strong field in both these, which means it creates a what? Creates a lot of torque. A lot of torque. And then it'll come up to speed. These guys won't have a tendency to run away because as it comes up to speed, the counter EMF goes down, which causes the motor to speed up. So you should never see a series motor ran with like a belt or anything like that. It should either direct drive or sometimes chain drive. Direct drive or chain drive.
So if it has a belt, you didn't mention that before,
Now what happens is that if you got power on this motor and you take the load off of it, it will run away on you. Now what happens when it runs away? So you got all these windings in the center, and when something spins, what happens to those windings? They try to do what? They tear apart, and these guys will literally sling themselves apart if you run them unloaded. Because what happens if the counter EMF goes down, then the speed of the motor goes up. And what's happened is as the counter EMF goes up, this guy here draws less current, which means this guy rear has less field current, which means less field current means less counter EMF, and these motors will just take off on them. So these guys are usually going to be direct drive, or they're going to be chain drive. Chain's not good. They like direct drive on these. Unfortunately, they do use belt drives. These guys have really good torque characteristics. So what happens, most drills use series motors. And so what happens, you got this thing spinning in the air, and you stick that thing in a piece of wood, and what happens when it gets caught on something? You ever had a drill in your hand when it gets caught on something? It will really rip itself out of your hand because it slows down. So what happens is you put it under load, it slows down. When it slows down, it creates more torque, right? You understand? The starter on your car is a what? Is a series motor, right? Tons of starting torque, right? Not really good speed regulation, but a bunch of good starting torque. So anything that needs a lot of starting torque is going to use a series motor. Vacuum cleaners use series motors. A lot of them. Some of them don't, but a lot of them use series motors. Because when you start those things up and you got it down inside your carpet, it's going to require a lot of watt starting torque. And you can hear that sucker change speeds when you move it across something, right? You're up here vacuuming and you're on a piece and you go on a carpet, you hear it go, it'll slow down. But why is it slowing down? Because it needs more watt. It needs more torque. So these guys create a ton of torque. They got crummy speed regulation. As soon as you load them down, they slow down, but they slow down in order to create good torque. Great starting and run torque. Very poor watt. Speed regulation. These guys will run on either AC or DC. So a lot of people call these universal motors. And we'll talk about how that works in a minute. Yeah, universal motor. That means these guys run on AC or DC. If you figure out the equivalent AC, a series motor will run on AC. You just got to be careful about what frequency the AC has to be, because it determines what we call the inductance. But yeah, using applications that require extremely high torque, power hand tools, combustion engine starters, vacuum cleaners, and small compressors. So we got one, but we got one over there. I need to find it. I can't find my stepping motor either. But yeah, let's take 5 minutes. Thank you. This is a DC motor you'll run into most often in the industry because you can control it so much. This is called a compound motor. Has high starting torque, good speed regulation. A cumulative compound motor, the series field aids the shunt field, high starting torque but less speed regulation, and the differential has less starting torque but better speed regulation. What's that? Shunt means shunt is a term we move. It's another term we use for in parallel. So a shunt field would be the parallel field. Are you okay? And these PowerPoints are up on. Yeah, we don't have. We don't have a book in this class, so these are your what? The PowerPoints are your book, right? Mechatronics, yeah. It's a big.
Will this information, will this be on our test or next test?
Yes. Which comes up when? Next Wednesday.
Is it?
You know, Monday's. Yeah, Monday's a holiday.
So is that, I looked the other day and I didn't see the test review for 2. Will it be up to?
It won't be up until we see how far we can get. We're supposed to get through the motors. Supposed to be through with motors already. But like I said, we've had a problem with this class. I've been holding off and not going at the speed the class needs to go because of the absenteeism in the class. Y'all did really good today. I think y'all. So speed control, armature. Voltage increase, speed increases, voltage decrease, speed decreases. Normally used because if the speed of the control circuit fails, the motor will stop. Some of our DC motors, if you lose the field while it's running, the motor will run away. And so what happens, instead of me controlling it with one motor, I control it with the field, the other motor I control it with this or that. Normally we control it with armature. Except for the series motor. Now the series motor, you can't split them up, right? You understand. But your shunt motor, your separately excited motor, your compound motors, we control those with the armature. Field or stator, voltage increases, speed decreases, and torque increases. Voltage decreases, speed increases, and torque decreases. Not normally used because if the speed control circuit fails on a shunt motor, separately excited motor, or compound motor, while in operation, the motor may overspeed. Now the problem is on these DC motors, you've got that wound rotor, right? You understand? And the higher the speed goes, those windings are trying to pull themselves apart, right? You understand? And they come up and pull themselves apart, and they get into the stator. The motor just tears up. We had a 200 horsepower motor out at U.S. Steel. It was a separately excited motor, and every once in a while that guy would run away, and it would just sling itself apart. And we never ever figured out. It had an overspeed sensor on it, so it had a centrifugal switch on it that was supposed to kick the motor out if the motor got up above a certain speed. We had speed feedback circuit, electronic circuits that monitored the speed, and it swung itself apart probably twice while I was out there. And we were the electronics guys, and we never figured out what was causing it. What's that? 200, I forgot what type of horses they were. They were the same type of horses that they did, and they were about the same weight when they did this. Oh, you never heard that's why we came up with horsepower? Just research the history of the horsepower, and it'll come up and it'll give you that. It'll tell you exactly what they did. Basically, they had to wait down in a well, so that way they wasn't working against friction. And then it came up across a pulley. And then they would say go, and they'd hit the horses, and then they'd start timing it and see how long it took them to get it to the top, because torque is rated. Work is what? It's force over distance, right? Force over distance. So I don't forgot the size of the weight, but it was a precise weight. And then they hooked it up to the steam engine and see how fast the steam engine could raise the same weight up to the same distance. And that's the way the horsepower came up to be. And unfortunately, that's what we use now, right? But the rest of the world has left horsepower because it's so hard to deal with, right? But most of the electricians understand horsepower. They say a 5 horsepower motor. Well, when it comes time to calculate your power bill, it's not easy. So this is the way we can control the speed. We can use electronic devices called SCRs. Now the problem with this is the first time we came up here is what we're trying to do is we're trying to control the current flow into the armature. What device do we use to control the current flow in a circuit? Resistors. So we had what we call a 5-speed crane, and what they did is they just had 5 resistors. Well, actually had 4. And what we would do with it is they would have relays across the resistors. And what would happen is that if all of them were closed, you got maximum speed, right? Because we bypassed all the resistors, and I would drop one in, add another resistor, and the motor would slow down. The problem is, though, resistors do work. So what you were doing is you're wasting a lot of energy in what heat. These resistors, guys, these guys had fins on them. They was inside a big old cage, so you couldn't touch them because they really got warm. They really got hot. And these were 5-speed cranes. And that's what they were, and that's the only thing you did. You could, if you was riding on the crane, you could hear the relay. You could hear the relays clicking, and while they was moving, and you had 5 speeds, and that was it, right? You understand? What we'd like to do is, and this would be with here we're controlling it with a pot that's wired as a rheostat. So what would happen is that as I slow the motor down, the motor would slow down, but the pot would get real hot, right? You understand? Because it's still going to produce that I²R, right? You understand that? So they said, okay, and this is controlling it with what we call a bipolar transistor, which is a current valve. And what this is this is a device that I can control the flow electronically. And so what happens is the more we move this toward the top, it would open the valve up, and it would let more come through. But it's still got an R value. It's just that now we're controlling the R electronically. So what would happen, you run these things at real low speeds, those transistors get hot again, right? You understand? So what they tried to do is, okay, let's come up with a method where we come up and we vary the voltage using another method. So what they did is they came over here and we took an AC signal like this, and we switched it up to both sides. Now the motor is going to average this out. Anybody know the formula? It's 2V peak over pi. And if we knew this peak value, we divided that by pi and multiplied that 2. That's what the DC motor would see, and the DC motor would run at that speed. So when we started using with these SCRs, it would come up here and we'd literally cut off the thing. And now what would happen to the average voltage? The average voltage would go down, and the motor run at a different speed. So with the SCRs, they were either fully on or what? Fully off. So fully on, they had almost no resistance, right? You understand? So they would drop little. They wouldn't get very hot. Now they're going to drop some, so the SCRs do get hot. Or we turn them off. When we turn them off, they conduct no current, right? You understand? So now we can control the speed with these SCRs. So most of your DC drives out there we use to control the speed is going to be SCR drives. Now these SCRs are still going to get hot because they might be controlled in a 200 horsepower motor, right? You understand? 200 horsepower motor, 746 watts per horsepower. You're talking about thousands of power, right? You understand that? And so when these guys here are on, if they drop 2 volts, well, 2 volts at 200 amps is still 400 watts of power. So these guys do drop a voltage, but they drop very little. That makes sense. So now I can electronically control with this thing. But the drives became very, very complex, especially if they were closed-loop drives. So what does closed-loop mean? We get feedback. So I'd set the motor. I say I want the motor to run at 200 RPM, and by George, they would adjust the firing angle of the SCR to average out, so the motor would run what? 200. If it tried to slow down, it would do what? It would increase the voltage automatically. If it tried to speed up, it would decrease it. So all these out at U.S. Steel where these were all closed loop systems. So them guys would set it at a certain speed, and by George, it would do what? So very complicated. Sooner or later, they realized that we could electronically control the speed of a DC by using something called pulse width modulation. So these are, oh yeah, everything on the Amtrol line, every motor that we control the speed over there, we can do with what we call pulse width modulation. So here we take a DC voltage, so we're going to have the DC power supply out there anyway to run our PLCs, right? You understand? But what we do is we pulse this thing. We don't change the frequency. So if I stop this, no matter where I stop it at, as soon as I start drawing on it, it'll stop. If you notice, let me use white. So this guy and this guy occurs exactly at the same spot. So that means we're not changing the frequency. All we're changing is the duration that this pulse is high. Now, what we would do is if we could measure what we call this guy right here, I'm going to have to change to a different color, guys. I can't get to my marker. There we go. So this would be a certain time period. Let's just say it was 100 milliseconds. We can figure out the frequency. Well, what happens is we can come over here, and what would be the percentage that we have right now? About 80%? Well, what would happen if I had pure DC, then this would be up here 100% of the time. Okay. If I come over here and if I start doing pulses like this, and I'll try to do these even, this would be up here 50% of the time. Okay, does that make sense? If I come over and look at this guy here is up here at this high value about 80% of the time. Well, what you do to calculate, and this works perfect, guys, is to calculate the average voltage. And we call this the duty cycle. So a 50% duty cycle would mean it's what? It's high 50% of the time and low 50% of the time. Well, what determines the speed is not the low, it's how long is high, right? You understand that? What time, how long are we putting voltage on there? Well, on the pulse width modulation, what you do is you just take this peak value. So if this peak value was 20 volts, and you had a 50% duty cycle, your motor would see it as 10 volts. If you had an 80% duty cycle, it would see it as 18 volts, right? You understand? So what I'm doing is I'm changing the speed of the motor just by changing the what? what we call the duty cycle. And that's the way you calculate the speed. You take your maximum voltage, you multiply it by the duty cycle, and that's what the motor would see.
We had it on the oscilloscope on Monday. You made it, I think, smaller. It slowed it down, and you made it bigger. It sped it up. The motor ended up on Monday.
This class?
Yeah. 200 look up.
No, all we were doing was just controlling the voltage. We weren't doing the duty cycle. So I got two methods. I can control the voltage, but if I have a fixed voltage of 24 volts, and then I control it with a resistor, what's the matter? Well, the resistor is going to produce power when you try to slow the motor down, right? You understand? Because it's going to drop the rest of the voltage. So if I got 24 volts over here, and I want to put 2 volts across the motor, and I use a resistor, then my resistor is going to drop what? 22 volts. V squared over R, right? You understand that? And that's the power formula, V squared over R. So what happens is the slower we run the motor using a resistor or a transistor that we're working in what we call as a resistor, then it's going to get real hot when the motor runs slow, and it's going to cool down when the motor runs, y'all understand that. Pulse width modulation, these devices are either what? They're either off or on. So it's like a light switch. So how much power does a light switch produce when it's on? It's got zero resistance, right? You understand? 10 amps times 0 is still 0 watts. So the switch does not produce any power. It's used in there to control the power, right? So all the power goes to the bulb. How many watts does it produce when the switch is turned off? 0, because now there's no current. So one way you have current, but you have no voltage. The other way you have voltage, but you have no what? No current. So if I can get these electronic devices and switch them off and on, right, you understand, an SCR can't work off DC, and SCR has got to work off AC. So I got to put AC across the SCR, and then it produces DC when you turn it on or off. This guy I can control with transistors, right, or different types of devices. Because what we're doing now, we're turning the transistors wide open, or we're turning the transistors off. When you turn them wide open, they drop very little voltage, right? You understand. When you turn them off, they have no current. So what we do is we use what we call pulse width modulation. I got a motor up here, guys. I'll hook it up, and we'll run it when we get back off our lunch break. But this guy right here, so what has happened is now is I can electronically produce pulse width modulation. So all your new PLCs, your programmable logic controllers, are going to have one of the outputs, at least one, that you can do what with. You can generate pulse width modulation out of it. Which means you can come up and you can control light, the brightness of lights, DC light. Well, lights don't care. You can easily control the brightness of an LED with this. You can control, or you can control the speed of a motor. Now, you can't run the motor off the PLC, and all this is a real little thing, right? You understand, but you can use that to run an electronic module that's designed to handle that for you. So we have pulse width modulation over there on our circuit. So what I'm going to do is I'm just going to come up here and take my function generator. So this function generator has the ability to generate, because we can do it electronically, right? You understand that? Pulse width modulation. So what I'm going to do is hook up my oscilloscope to this. And what's nice about an oscilloscope, and of course what I'll probably do is get a DC meter. I get a DC meter, it'll actually show you as the pulse width goes up, the DC voltage goes what? Up. So down here on a function generator is electronically created. We have 3 different signals we can tell it to generate. We can show it to generate what we call a sine wave. This is a pulse waveform, which is what I'm going to turn it on. Okay. And then, of course, it comes up here. This is a pulse waveform. And what I'm going to do is take my volts per division and turn it up, right? So how do we read this thing, guys? Let me throw it up full screen. Let me move it back a little bit. Yeah, what's my oscilloscope telling me? Well, scopes do two things for us. What's the two things it does? Measures what? Voltage. No, scopes don't measure, can't measure current. Relative to time. So your scope measures a waveform relative to time. So what we have is we have what we call the horizontal control, which is the control that goes this way, right? You understand that? And I come up here and I set a speed. So right now, can y'all see my speed right here? That's 500 microseconds for every major division. So you can see the scope is up here in a major division. So right now, I could come up here. So this would be one cycle from here to here, right? You understand? Oops, let me get it up there.
When you say division, what is the?
These are the divisions, the big white line. These are major divisions. These are minor divisions. So every major division is split into 5 minor divisions. So when I come down here and get this 500 microseconds, that's not for a minor division. That's 500 microseconds for every major division. Y'all understand? So if I wanted to know the time, first of all, I get my one of my edges on one of my vertical lines. You'll see that? So I could get it on any vertical line. It wouldn't make any difference. And then I would measure to the next vertical line, and that would give me the time. So I'd go 1, 2, 3, 4, 5, and this is going to be 0.15 because it's right in the center. Y'all see that?
So you're measuring
from this edge. So the scope, the speed is referenced, time is referenced from the left to right. So what's on the display on the left occurs before what it is on the right. So normally when we measure time, we try to get the left edge, either this is what we call the positive going edge, which we're talking about on the duty cycle, right? You understand? So I'm gonna line this up. I'm gonna move this until that thing gets up to one of my vertical lines. Now I have a reference point to measure from, right? You understand? If I come up here and try to measure that, how many divisions is that? Well, that's real hard to say because I got minor divisions on both sides. So what we do is we come up here and we move it with what we call our horizontal position. So this is my position. Yeah, this is my position. This is this is where I set my speed, right? You understand? Okay. So what I'm going to do is I'm not looking at that arrow right now. So this is where I start from, right? You understand that? And then if you know 500 microseconds per division, and this is going to work out, then you just say this would be 500. That'd be 1,000, right? Or 1 millisecond, right? Right? So every 2 would be 1 millisecond. So after a while, what you learn is you learn how to read it without using a calculator. What most people do when they're learning is they'll count the number of divisions. They'll go, 1, 2, 3, 4, 5. Now the problem is, I would say 5.2. Now why am I saying 2? Because there's 5 marks that I'm counting in ones, right? You understand? So if I'm counting in ones and I take 1 and divide it by 5, that's going to be 0.2. So I would come up here, I'd say 1, 2, 3, 4, 5, 0.2 divisions, right? Y'all see that because it's 1 mark, and then it's half a mark. Well, wherever you start here, I could start with this guy if I wanted to. It's just that what you do is you choose the same spot on both your, okay. So here I'm starting on the what? On the one going up. So I count to the next one going up. Let's redo it because the frequency is the same. Let's say I come up here and reference it to one of my low going edges. It's still what? 1, 2, 3, 4, 5.2. It's still the same because the frequency is the same. So it's up to you which side you reference to. But whatever side you reference to, you count to the next one on that same side, right? You understand? On a sine wave, you'd make sure you did it at the same spot. These pulse waveforms, we don't worry about that.
So what's that number there that keeps moving?
This shows me my position, and it shows me my actual time in milliseconds. So this is a computer. This is a digital storage scope, so it's got a computer in it. I should turn that off, so this is actually giving me the time for one cycle. That makes sense? But we don't need to see that. We need to see if we can do it ourselves, right? So what would be my time? 1, 2, 3, 4, 5.25, right? Because I'm halfway through. Multiply that times that, and that should give me my time. Actually, it should be 0.5. What was it? 1, 2, 3, 4, 5.21. What it should be. Is that right? 2.6, about 2.6 milliseconds. Are you okay? Yeah. There's one of these on the next test, guys. Y'all need to get this down. How to measure the speed and the voltage.
And you said, Mr. Rick, the little...
No, this is wrong. I don't know what that is. We can make it measure time for us, but that's not good. Go ahead.
So you said the little line in the middle, that's 5 of them, right? Can you divide that by...
No, we're counting in ones. So I'm counting in ones. If this is equal to 1, what's that guy right there equal to? 0.2. Okay. So this would be 0.2, 0.4, 0.6, 0.8, and then I make the other 9. So if this is equal to 0.2, what would half of it be? That would be a 0.1, 2.1, right? If this was 2, that would be 4. So what would be? It would be 0.5, right? 0.25. In fact, it's lined up on 2. It's lined up perfect now. What's that? It would be half of a division, right? Yeah, it is. It's 0.4. It's 0.4. If this is a 1, then each one of these lines has to be worth a 0.2. 0.2, 0.4, 0.6, 0.8, and then that would be there. So now it's lined up. So that would be 5.4. Right? You understand that? Huh?
Earlier we were saying it was between 2 points. And we got 10.5. And we got it was between 2 and 4, 0.3, right? I don't think it would be half of what you did. You were trying to half out one of the divisions. The smaller division.
The problem we have with an oscilloscope is not perfect. So it's up to you what you want to do. Normally what people do, they either round it up or round it down. Because it's going to be close enough to what?
But it looks to me like 1, 2, 3, 4, 5,
0.4. Each minor division is worth a 0.2. Yeah, so there's 2 minor divisions, so what would that be? 0.4, right. 5.4. Well, if you say 5 times 500, you come up and get 2,500, right? Micro, and that's not legal engineer notation. So what would we say? We'd use milli, right? Move the decimal point over 1 and say milli, right? I mean, sorry, 3. Oops.
When you say for the test, you mean like right then, you said that, you mean that we're gonna need to calculate
The time.
some of these,
There's only gonna be one. There's only one question on the test. This is a Siemens question too. So this came off the Siemens.
And that's even says on Blackboard also, will you take that or no?
You have to pay for that.
Oh, that's
You got to pay for taking the Siemens test. Now, what we had, and we wasn't really sure. We were provided, and we were provided by somebody else. Gave us a copy of a Siemens test. Now, what we were told is that everything they cover is going to be on the same on each test. But they said they covered a test bank. So just because you had this one that measured a certain frequency or a certain period, it might necessarily be the same one you have on the test. But Milton told me they were the same questions on the sample test that we have. So the questions that have almost every question on my test that has a graphic image on it came off of the Siemens test that we had available to us. So what it means is that they expect you to have a little bit of knowledge of trying to read an oscilloscope. Now, what advantage does an oscilloscope have over a meter? An oscilloscope shows you what's there relative to time. A meter does what? It averages everything out. What would my meter measure if I put it on this thing right now? It's going to measure 0. Because this is not DC, guys. This is AC. I don't know if y'all can see my channel 1 marker right there. So this is 0 reference right here. Okay. And what a meter does when it sees AC, it averages out and it gives you 0. So if I wanted to make this DC, then I would have to come up and change it a little bit. So a digital meter or meter averages everything. So what you see is you see the average. You don't actually see what's there, right? But an oscilloscope shows you what's there. So yeah, like I said, if I put a DC meter across this right now, it'd show me 0. So what I did is I changed the frequency, or I changed the time, which is the frequency. So what would it be now? What I'm going to do is try to make it spread it out as far as I possibly can. This is when you're so if I try to measure the time now, I can't measure it, right? Because I'm trying to cram so much stuff into one unit. So what I'm doing is I'm coming up here and increasing the speed of my scope, which means the time goes down. And what I'm shooting for is I'm shooting for 1 cycle. So I got 1 cycle. So we call this a cycle. 1 repetition we call a cycle. Oh no, we'll look at that. So now this is 250 microseconds per division. 0.8. 4 divisions. These 4 words. This is 4 divisions. So this would be 1, 2, 3, 4, 5, 6, 7, 8. Right? 0.8. 8.8. Huh? Yeah, that's crossing on the line. 8. No, that's right on there. Yeah, guys, and what I was telling you, scopes are, if I wanted to measure the frequency, I'd use a digital device called a frequency counter. What we do with an oscilloscope is an oscilloscope's fairly accurate, but it's not perfect accurate because of these minor divisions. So guys, if it's out here past a mark, we usually just round it, right? You understand? So if it's closer to the one on the right, we'll count another 0.2. If it's closer to the one on the left, we'll leave off at 0.2. And it's going to be accurate enough so you can figure out what's going on, right? You understand that?
You said that 8.8 multiplied by 250.
Time 250 microseconds, and that would give us our time. What would be the voltage? Well, the voltage is the same way. I've got mine on 500 millivolts per division, so voltage is this way. So what I'm going to do is I'm going to take it now. I'm not interested in the time. I'm just interested in the amplitude. So I've got my bottom, since we count up, I've got my bottom on a horizontal line now, right? You understand that? And I just count the number of divisions, right? 500 millivolts per division. What would that be? Looks like it's 5.2. One, no, it's 4. 1, 2, 3, 4. 0.2. Well, if I take a 2, 0.2 and multiply it times 5, I'm going to come up and get a 2.5, right? So it's 2.25 volts. Huh? 0.2. Well, if I multiply, if I multiply 2 times this, it's going to give me a 1. You're right. So what we came up with get? 2.2 volts. Are we okay? Yes or no? 2.2. 2 point. What's that? Would it be 2.2 or 2.1? 2.2 or 2.1? I think the way it's written, it's going to be obvious which one's the right answer. Hopefully. I can't remember. So I'm going to go 1, 2. So this is 1 volt. That's 2 volts, right? So what I'm seeing is I'm seeing a 0.2. So what we do is we multiply that times this. Yeah, it's going to be. No, I'm not always right. So are y'all okay on that?
So you said it's a 0.1 class right there in between the street?
It's on one. It's on one division. Yeah, each one of these. If this is 500 millivolts, so that means each one of these should be worth 100 millivolts, and that's what I would look at. So what I do when I measure scope, I've been using these so long, I don't multiply in my head. I count. So here I would say 501, 502, right? Understand? And then I know each one of these minor divisions would, if it's 500 millivolts per division, that means each minor division has to be worth 100 millivolts. So I would have came up with right off the bat. So 2.1 volts.
So you said, Mr. Reed, I know you said that little dash will be.
These are minor divisions.
Minor divisions. They're 1 millivolt, 100 millivolts.
Right. If I did it without a meter, now what when people get in AC, the easiest way to teach it is to count the number of divisions and then multiply it by your scale. That's the easiest way to teach it. But over time, you learn how to read these things without even thinking about it because you read them, right? You understand. So like on this, normally this guy gives us a little problems because this guy uses this 250. Just about all scopes goes in 1s, 2s, or 5s. This guy has this 250, which screws me up, 2.5. But all your other scopes goes in 1s, 2s, or 5s. And how many can y'all count in 1s, 2s, or 5s? Yeah, every one of you learn how to count in 1s, 2s, and 5s in elementary school, right? So what I'm saying is I know it's 500 millivolts per division, so I'm counting in 5, right? You don't understand. So I'd say 500, 1, 500, 2, and then if it's 500 millivolts per division, then I know each one of these minor divisions has to be worth 100 millivolts, right? Y'all understand that? So it would be what? We ain't got it right yet. What did we say? So let's do it one way. I'm coming up with 600 millivolts, guys. I don't know. I'm coming up with 600 millivolts. I'm sorry. That would be right. I'm sorry. This would be what? 1 volt. This would be 2 volts. This would be 0.1, right? 2.1. Are we okay? And the time, what I would do is I would come over here and I would do what? I would line it up on a vertical line, and then I would go what? 250, 500, 750, right? You understand? 200, and that's the way I would start up and count. Everybody okay? It's just what's so hard on this. 250 millivolts, what would each one of these minor divisions be worth? That would be where I would run into a problem.
So what did you get for them, Mr. Rick? So it's not 4.5, what is it?
It's
4.
It's 2.1 volts. For what? Time or amplitude?
The volt.
Well, the way I showed you take the number of major divisions, right? You understand? And then count the number of minor divisions. But the minor divisions, if we count in ones, then each minor division has to be worth a 0.2. So I'd say 1, 2, 3, 4.2. Then I would multiply that by 0.5, which is 500 millivolts.
Okay.
Then you come up with what? 2.1 volts. Well, what I'm saying, over time, you learn the units, right? You understand? You have in your mind what each minor division is worth.
Over time, you divide and both
No, we multiply both of them. So over here, what would be the time? I would say 1. So I've got it on 250 microseconds per division. So I'd go 1, 2, 3, 4, 5, 6, 7, 8.2468. 8.8 and multiply it times 250 microseconds, and that would give me the time.
Okay, so I'm gonna try to throw it up right after that. If you're only counting the 5 point square as 1, then why, when you go to the last one, you double it? You understand the question, you know what I'm saying?
Yeah, everybody has this problem.
Because you're not doubling.
Okay, no,
singular
watch
square.
this. So what we're doing, we're counting these as ones. No matter what we're sitting on, we're counting these as ones. And then we got 1, 2, 3, 4, 5 divisions. So if this right here is equal to a 1, what would this be equal to? A 0.2. That would be 0.4. That would be 0.6. This would be 0.8. And then that would be the next division, right? You understand? So what we're doing is we're counting in ones. We're not counting by the value here. We're counting in ones. So what is 1 divided? I'm going to take 1 and I'm going to divide it into 5 divisions. So what's 1 divided by 5? 0.2. So if I'm counting in ones, then that means each one of these minor divisions has to be worth a 0.2.
Right.
Okay, so I go 1, 2, 3, 4, 5, 6, 7, 8. 0.2, 0.4, 0.6, 0.8. 8.8. Then I take that. So I haven't even looked down here at this yet, because this tells me how the time per big division, right? So I count the number of this, and I use what for each minor division? I use a 0.2 for each minor division. I take my number of divisions, I multiply it by that, and that gives me the time. And that's what I'm saying. 250 microseconds, it would be hard for me to figure out what so each one of these would be worth a what? 0.5? Yeah. But that's what I'm saying. And what you do when you count is you don't have to worry about how to figure out what this is equal to, right? So if I got 250 microseconds per division, that means each one of these guys should be worth what? 50 microseconds. And now I got to do all this garbage in my head. So what we do here is we just do what? Count the number of divisions, right? And since we're counting in ones, then what each one of these should be worth? 0.2. And then I multiply it. So if I was going this way, I'd go 1, 2, 3, 4, 0.2. 4.2. Then now I'm interested in this, right? You understand? Then I take the number of divisions and I multiply it by the scale, and it'll tell me what I measured. We okay? Okay. So here, what do we come up with here? 1, 2, 3, 4, 5, 6, 7, 8.2468. So that's 8.8. I'm going to multiply that times 250 microseconds, right? And that should give me the time. So what would be the time? I'm waiting. What's that? 2.2 milliseconds. Everybody okay? What would be the frequency? I don't know. I'm not doing it. That's what Anthony said. Y'all, you check his word, right? 2 point.
So for the time, you got 8.8.
You got it? Okay? Yeah, y'all have to get, scopes do not use, test equipment does not use legal engineer notation. You probably noticed that on your meter. Like in DC, it jumps, if you got a 2,000 count meter, it means when you get up to 199 ohms, it jumps to K. And then you'll see put down 0.25 K, right? So test equipment does not use legal engineer notation because they're limited in the number of ranges. Plus digital meters don't count in tens. It counts, we have what we call a 2,000 count meter, which means it's going to range on 199, right? We have a 4,000 count meter, which means it's going to range on 3,999, right? And then we have a 6,000 count meter, which is very expensive, which means it's going to range on fives, right? You understand? So that means your meters are not going to use legal engineer notation. We require you to use engineer notation. So if you put 0.356 kiloohms, then technically that's the wrong answer, right? You understand? But your meter has ranged on you, right? You understand? So what would 0.235 kiloohms be? It's going to be 250 ohms, right? You understand that? But we have that big problem in DC because people want to write down exactly what their meter tells them. So here, this is microseconds. So people want to write their answer in microseconds, and they'll put 2,560 microseconds, right? You understand? Technically, the answer is correct. But it's not correct if you use correct engineer notation, which is what we require y'all to use, right? So what do we come up with here? Okay, so what we do is we call one of these, one repetition, we call this a cycle. One repetition of a repetitive waveform. So these things are constantly happening over and over and over and over and over and over and over again as long as I have power on, right? You understand? So this right here, if I go from rising edge to rising edge, that would be one cycle. Now these cycles are occurring at a rate. The rate that the cycles occur in, we call that the frequency. So Alabama Power generates 60 cycles per second. From a reference point. So if I'm measuring time, we wouldn't try to measure time with my scope set up like this. Because why? I'm trying to put too much information and eventually it'll come up and look just like I'm trying to put too much information inside a thing, right? You understand? So what we do is we speed up our scope, which means less time per division, and then what will happen is these guys will come up here and start spreading out. Now my ultimate goal is to get one cycle on my screen because that's when my scope is going to be the most accurate. So that means I'm going to slow this thing down, which means I'm going to put more time per, now I can see one cycle. If I go right here, then my scope is less accurate because I'm trying to put too much information inside of what? Inside a single division. So my ultimate goal is to set my speed of my scope, which is in time. So if speed goes up, time goes down, right? You understand? So notice if I go to the left, my scope goes slow, right? You understand? If I go to the right, my scope goes faster. Now, of course, it looks to me like DC. Because now my scope's got it spread over, got my high spread out over more than the scope can see. So we used to teach a digital troubleshooting class, and you'd be surprised how many people drew a DC level when all they had was they had their scope going too fast, right? You understand? So one thing you need to do, if it looks like DC, you need to slow it down to make sure it is DC, right? So this is the best I would do. Now the next thing I'm going to do is now I can't measure the voltage. Why? Because it's going off the top and the bottom of my screen. I can't measure the voltage now because I'm trying to put too much information inside a single scale, right? So what do I do on my voltage? Well, I turn it up as high as I possibly can and still keep it on the screen. Right, you understand? So I put less volts per division. So this is the best I can do on this waveform right here, is I can see, I turn it till I can see what? One cycle, and then I adjust the voltage till I can maintain it on the screen. That makes sense? Okay. Now my scope is as accurate as it could possibly be. Is it as accurate as a meter? No. But it shows me what's there, right? You understand? And like I said, a meter will average. So if I wanted to get an average, the actual voltage of a battery, I wouldn't use an oscilloscope. I'd use my what? I would use my meter, right? Because my meter is really accurate on DC. Are we okay? Yes or no? So what did we come up with? What was our time? I didn't change my speed. So what would be my time? 2.2 milliseconds. So as the time goes down, the frequency is going up, right? These guys are the inverse of each other. So if I wanted to take the frequency, I'd just take what we call the reciprocal. We use the reciprocal all the time. What does the reciprocal give you? It gives you the exact opposite. Frequency and time are exactly opposite from each other. So if I take that 2.1 milliseconds and take the reciprocal of it, it would tell me what frequency I'm looking at. So my scope doesn't measure frequency, it measures time, but we very easily can calculate frequency, right? Of course, we can make this scope measure. So what do we come up with our frequency? The reciprocal.
4, 5, 4, 5, I mean, we changed that to.
Yeah, now this is a function generator. And that's what it's showing me. It's showing me the frequency. So this has a frequency counter in it, right? You understand? Your scope don't have that. So if I measured Alabama Power, our cycles would be 16.66 milliseconds. If I took the reciprocal of that, it would give me 60, right? You understand? So if I wanted to measure the frequency, I would use a frequency counter. If I wanted to get a good idea of what the frequency was, I could use an oscilloscope. And an oscilloscope's going to get you close enough so you know if it's what, right or wrong. Huh?
So on the test, if they ask us to find the time,
They ask you to find the frequency, but they give you the time. So they give you they give you the scope display. They tell you what the controls are set on. They tell you what the voltage per division is set on and the time per division. You measure one cycle, the time for one cycle, and then what do?
you
Hit the receptacle, and that'll give you the frequency.
There's nothing else.
Huh?
I just have to review.
So scopes, and I can make, this is a computer. So I could tell this computer to display the frequency for me. But that's this guy right here. This is $450 for that guy right there. I can get an oscilloscope, an analog oscilloscope that does exactly the same thing for probably less than $200. So you're going to run into a lot of analog scopes out there because they're what? They do the same thing that you should know how to do, right? You understand? They just don't do all the math for you. So yeah, this guy's a computer. I can tell it to display frequency, I think. I'd have to figure out how to do it. Oh, I can put a cursor up there. I'll figure it out later on. I don't ever use it anyway. So what I'm doing now is I'm going to come up here and I'm going to tell my function generator to control the duty cycle. Can y'all see that? So I'm going to turn that on. And what you should notice is the frequency did not change. So if I counted the number of divisions, it should come up and give me the same. But what I can do now is I can change the what?
So how, what?
So notice, if I don't know if I might have changed the frequency a little bit. But what I want you to notice is this rising edge and this rising edge don't change. Oops.
You didn't really change anything, nothing changed.
I'm not changing the frequency. I'm not changing the frequency. I'm not changing the time, what we call the period. What I'm changing is the percent of the time that it's high. So what we could do, especially if I put this 1, 2, 3, 4, 5, 6, 7, 8, 9. What I'm going to do is I'm going to change my frequency to make it real easy. I'm going to come over here and put it over 10 divisions. So 1, 2, 3, 4, 5, 6, 7, 8, 9. I need to. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 divisions. So what's going to really make? So right now, I would be running an 80% duty cycle because it's over what? 8 divisions, right? So what would happen is the closer I get to this, the faster the motor would run. So that's the best I can do here. That would be what we call a 90% duty cycle. And then I come over here and I adjust it down here, and the motor would do what? It would slow down. That would be a 10% duty cycle. So at 10%, 1, 2, 3, 4 volts. At 10%, my motor would see this at 1 volt. And it would run at whatever speed 1 volt would tell it to run at, right? Here it would run at what? It would see it as what? 2 volts. Here it would see it as what? 3 volts, right? So let's get one of our meters. You got us upset the other day, Krista. One of our meters was missing in a box.
Oh. I put it back. I was like, I need to put it back.
Yeah, you do. That's what.
Yeah.
So I called Nancy and said, "One of our meters is missing."
Oh no, I'm sorry.
That's okay. I went over and found it. She was happy when I found it. First of all, guys, I'm going to have to make this DC, so this makes some sense. So I'm going to come up here and So what I'm going to do is I'm going to move my ground reference on my 0 volt reference on my scope down here so we can see it better. And then I'm going to make this DC. And then we're going to hook up a meter to this. So I got 1, 2, 3, 4 volts, right? So right now, what should it measure? Yeah, so we got a 40% duty cycle, so it should measure. So 4, what? And this is all we're doing is just showing how we can control the speed of a DC motor using what we refer to as pulse width modulation. And this is the way they do it now, guys. Yeah, I got 500 millivolts per division. I got 4 divisions, which gives us.
Is that 4 division or 4?
Okay, so it's 2 volts. I'm sorry.
So it is 2?
Yeah. So who said Rich never makes mistakes? Anthony said that?
But you may make one, but you fix yourself right quick, Mr. Rich.
Well, what's nice is I know when it's wrong, right?
Yeah.
The meter's not working. It might be the meter's not doing what it needs to do. So I got it on volts. I got it. Oh, okay. Sorry. I'm not on the right page. Okay, so we got 2 volts. What do you think my meter measures? So I take 2 volts, right? And then I multiply it times the duty cycle, which would be a percentage. So we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I did this so we could prove it, right? You understand? So 1, 2, 3, 4, 5. That is pretty close to a 50% duty cycle, right? So what should my meter measure? It looks like it's a little over. Let me adjust the output just a little bit. Nope, that's as low as I can go. What? Yeah, but I don't know if you can see it or not. It's a little over that. Yeah, so this is what the meter's measuring right here. Yeah, about 1.2 volts. Right.
So if you move
Yeah, what we're going to do is we're going to increase the duty cycle. So let's move the meter back so we can see both of them at the same time. And of course it's going to focus in on the meter, but you can see my duty cycle. So what I'm going to do is I'm going to increase the duty cycle and the voltage should go up. Isn't that sweet? And then I'm going to decrease the duty cycle and the voltage does what? So this is what your DC motor would see. It would see this average. It wouldn't see this frequency. It would see this average. So what I can do now is I can electronically control the speed of a DC motor using what we call pulse width modulation. Now I can't run a motor off this little function generator because it don't put out enough energy. But I can bring this to a solid state device like a transistor, which we'll try to do when we go. I'll show y'all these when we get back from lunch, and how I can control the speed of a DC motor. Not with pulse width modulation. This is the first time I showed y'all pulse width modulation. We had it, but we controlled it with the output of my power supply. So what we were doing is we were changing the output of my power supply. Now that would be pretty efficient, but then I couldn't use the same power supply to run my PLC that I run my motors with, right? You understand? So what we have is we have a fixed power supply on our PLCs, and then we have a nice power supply that's running the line and also running the PLC, and it's going to be a fixed DC power supply. Well, I can run this to a pulse width modulation circuit, right? You understand that, and then I can adjust the speed. And so every one of the motors that we have over on the Amatro line, the one on the Festo line, they all run off a fixed speed. The one on the Amatro line, we have a little pulse width modulation circuit on there, a little old tiny thing that we can adjust it between 0 up to a 9, whatever speed that is. And if we actually looked at the voltage going out to the motor, we would see that it's using what? It's using this pulse width modulation. So aren't that sweet? I mean, you can actually see it really good here. And like I said, when y'all get back, we'll run a motor off this. We got a little bitty motor up here. And you can see I can control what? I can control it precisely, right? So that would be half voltage right there if that was perfectly 50%, you know. We said 2, but I don't know if y'all can see it's a little above the 2 mark. So what I can do now is I can control the speed, but we can do this electronically. Because what I'm doing is I'm turning on these solid state devices, I'm turning them wide open, which means they don't produce a lot of power because they have very low resistance, or I turn them off. So now we can control a lot of power with devices that are not that big, right? You understand? Which is really, really cool. And this is the method I use. And like I said, every PLC, I don't know about the 1500s, but I know the 314s, the Siemens 314s have a pulse width modulation output on them. And also the little 1200 PLCs we have, and also the 1100 PLCs that we're using in advanced PLCs. Those have pulse width modulation outputs on them. Yeah, what you do is you would come in and you could use a digital input where you'd come over here and you'd flip a bunch of switches and say, I want this thing to run at 200 RPM, and then it would do the calculation to run it. It could do it open loop, right? Open loop means we take for granted the speed the motor's running at 50% speed. But what happens, any motor you load down, what's going to do? It's going to slow down. So what would happen is we would use like an encoder or something to bring back the speed and put a closed loop in there, and then we set in a set point. So the way a closed loop system works is we'll come in, and this is just we'll come in and we'll put a set point. This is what we want, right? You understand? And then it comes back, then we bring back a what? Feedback. And then we go through all the electronics that run the thing. But out here on our actual actuator, we're going to have some type of what? We're going to have some type of sensor. And that's going to give us the feedback. So I come in and I'll put a set point in, right, that generates an error. And then what it does, it turns the thing on, and if the set point and the feedback don't match, what does it do? It either speeds it up or what? Slows it down. And a perfect example is your cruise control on your car. So you're cruising along, you want to go 60 miles an hour, you hit a button when you get up to 60, and that's your what? That's your set point.
You can go past 60.
What's that?
You know, you said at 60 you can go past that, and off the gas and go back to 60, right?
Well, the car now your engine control module is controlling how much gas goes into your fuel injectors instead of the gas pedal. A lot of them you can feel, on the old ones you could literally feel the gas pedal will go down and the gas pedal will come back. I don't think you do that now. I think it's all electronically. Yeah, I mean it's all electronically. So like I said, on the old cruise control, I don't know if you remember those, you could literally, when it needed gas, you could see the gas pedal go down, and when it came off, the gas pedal would come back up. Of course, you can override it by doing what? By hitting the gas pedal, and then what you're doing is you're not changing your set point. You're manually putting more gas in to cause your. So you'll do that, right? You'll have your cruise control on there, and you need to pass somebody. What do? You mash the gas, and as soon as you get past them, you let it off. I had a guy one time. He used his dang the thing on the. He would turn his he would hit the plus and the minus on there to change the speed. He wouldn't use his gas pedal. So he hit the plus and he'd go back in our seat and he'd hit the minus. So the whole time we were driving, we were doing this. Yeah, because when he wanted to pass, he would press the plus button, right? You understand? You're supposed to use that to trim it, right? And then when he wanted to slow down, he used the minus button. He never touched the gas pedal. So I wanted to slap him. Yeah, because we was trying to sleep back there, you know. He was trying to wake us up. So everybody okay on pulse width modulation? It's really slick, ain't it? Really slick. Like I said, we've got little boxes up there on the Amatro line. In fact, let's go over and look. So DC reversing, we got two reversers over there. Reverse the electrical connection of the armature, not the field. This is the normal way we reverse a DC motor because the reversing circuit fails. The motor might not stop if it's a shunt motor. Reverse armature connection. What really gets people confused is that if you reverse both of them, the motor don't change direction. If you change the orientation of the field and the armature. So what you got to do is change one of them. Leave the other one alone. So normally on DC motors, we change the armature. The motor will not reverse if both the field and the armature circuit is reversed. I guess that should be an OR. So here's some reversing circuits. These are using bipolar transistors. We can do this electronically. So what we do is we could do it this way. So this is probably better to look at. We could do it this way, and what they're doing is they're using what we call a single pole double throw. We're using a double pole double throw contact or relay. Now the problem with this is that the motor's going to run, and when you flip it, it's going to reverse just like that. We call it plugging. We don't like plugging a motor. We don't like changing the direction of a motor without bringing it to a complete stop. Anybody have ceiling fans at their house? You ever reverse the direction and listen to that motor without it stopping? What does it do? Because it's pulling tons of current trying to reverse it, right? Understand? So normally what we like to do is we like to have a method of removing voltage from the motor altogether. So I could come up here and add another relay down here that cuts off the power when I try to reverse it, but that's a bunch of trouble. So what we normally use is we use a control called an H control. You see how I got that name, right? Even though it don't look like an H. So what we do is we don't ever bring it in there together at the same time. If you do, you're going to have a short circuit. Hey, boss. But look, if we close this switch and we close this switch, then how would the current flow? Then the current would flow up and would go through the motor in this direction, right? Y'all see that? And then if I wanted to stop it, what would I do? I would just open up both of them. That makes sense? And the motor would do what? That would be able to come to a stop. That's probably the easiest way to do it instead of trying to raise it. Don't want to do that. So if I come over here and close this one that they're calling reverse, and what's going to run clockwise or counterclockwise? Reversing means we just change the direction that it runs in, right? You understand that? Then I would come over here if I close these two. So last time the current flow was through the armature that direction. So now the current flow is going to be in what? In that direction. And go back. And we call this an H control. And that's what we got back here. So you notice every one of them, but it requires two relays, right? Y'all understand that? And every one of our lines over here on the Amatro line, you'll see every one of them that has the ability to reverse has two relays out there. This is bad. We don't usually. I've seen this used sometime, but the problem is you're running it forward and you change the relay and it flops over and it plugs the motor.
Yeah, but that way you end up somebody put it on forward inverter.
You can't put it on forward inverter at the same time. We interlock these things in all different types of ways. So what we do is we'll take the relay like this. And then what we do is, so this would be forward. This right here would be reverse, right? This would be the relay, not the motor. And this is coming out of the PLC. And then we would come over here, and this right here would be connected to minus. Well, what I do is I put over here, I put a reverse contact in my forward, and then I put a normally closed forward contact in my reverse. No, this is outside. This would be at the relays. This wouldn't be in the PLC. Now, I would probably program it in the PLC too, but no, these are going to be literally mechanical contacts on there. So if my program screwed up, right, you understand, or I accidentally made a mistake, if I close this guy right here and this guy at the same time, I got a short circuit. So what we do is we put electrical interlocks on the thing. Now, another thing they do is they put mechanical interlocks on the thing too. This keeps you from really screwing up and going in and mechanically pushing in both of them at the same time. So the best way to do it, and this is not in the PLC, this is out on the relay, right? You understand that? The best way to do is use both mechanical and electrical interlocks. By using bipolar transistors, so we turn these two on to make it run in one direction. You turn these two on and make it run in another direction. This would be using what we call power MOSFETs. So we can electronically control this. And then we can use pulse width modulation. So we could use this to control the direction, and then my power supply could be using what? Instead of plus 12 up here, it could be using what? It could be using pulse width modulation, so we can kill two birds with one stone. Your PLC doesn't have this capabilities, so normally what you do is you use your PLC to do what? Control the relays that's controlling this H controller here. I shouldn't erase that, was good. But what we do is we'd have one relay that we call what? So if it on a PLC, it would probably look something like this. We would use one of our outputs, which Stevens calls outputs. I say 0. And then this output would come over here. And then we would have our relay out here. And then this might be output 1. And then if this one is extend, then the other one would probably be what? Retract. I think. And then this would actually be a physical contact, and this would be R, and this would be E, or whatever you want to call it. And this is the way we would wire it up. Now, if it was a motor starter is a relay that has an overload. What we would do is then the overload is actually over here on this side. This would be the overload. And this would be one of the outputs on my PLC. And this is the way we would wire them. And of course, our PLC is using source and outputs. So that means this guy right here is going to give me the plus. So what would we connect over here? We would connect minus, right? So all our PLCs that we have in here is using syncing inputs and source and outputs. And of course, what's between here and my inputs, so my inputs are on this side, is over here we have that control logic, right? Those programs that are deciding what this input means. And here we're not going to teach. We might look at a PLC program just to give you an idea, but we're not going to do any programming. So this is what we're doing. We're troubleshooting from where? From this side over here, right? How do we connect up to the PLC, right? You understand that? So if I'm running syncing inputs, I know it's almost time for y'all to go now. That means my input devices, my sensor, whatever it is, right, is going to be using a what? This has got to have a plus, right? That makes sense? So our PLC is set up for syncing inputs, which means its inputs is referenced to the minus. So it means all my sensors are going to have to be referenced to the positive, right? So a syncing PLC input requires a sourcing input device. And this is pretty standard in the US, guys, if you're not using AC. Syncing and sourcing, by the way, only comes into play when you're dealing with DC. Because AC has no polarity. Y'all understand that? Because it's changing what? Changing so fast. So a syncing PLC input requires a sourcing, requires your input devices to be sourcing. And then, of course, a sourcing output requires your output devices to be syncing, right? Connected sync, right? You understand that? And then what we'll talk about later is we'll talk about these motors called stepping. So when y'all get back, what we'll do is, even though we're not going to lecture on stepping motors today, I'll run one just to give you an idea of what we can do with those things. And then I'll show y'all pulse width modulation, how to control, I will actually control the speed of the motor, and then we'll do lab. We're going to lunch. We're taking a 30-minute break. Are we okay? All right. See y'all in 30 minutes. So what I'm doing is I'm taking the output of my function generator, which is this electronic device down here. It gives me the ability to generate electronic signals. So we got it on pulse, right? And then we have it set for DC. And this is the signal I'm getting, and the scope's having problems triggering. Let me check sure. Oh, no wonder. So let's trigger on channel 1. Okay, here we go. So that should make it work okay. You need me? Yeah, what?
Right now, some of the same tight lines that we have need to be SNC. I don't know if we want to look into it, but they got some, they're like sort beads, so it could be sort of plastic. Recycle it, so it'll take all the colors and sort them out, put them in the color. So, and this is a robot, a mobile robot.
Yeah.
So I thought we might want to look at that. They also have Kuka and Yakasawa Motor Man.
So he's looking into that for me, and he's gonna give me some information on it. But I told him to just go ahead and leave me the catalog and that I would get it to you. But we order SMC parts, I think, every once in a while, cause wasn't that a SMC valve that we had to have for the motor, for the Fanuc? So I went ahead and got him to give me the catalogs for SMC. Not that we're going away from Festo.
You need to look at that grant for the cities.
Yeah, for the
She sent us another
certification,
letter
I did
about
see
what the
that,
status was. know
I
she
did
sent
see
it
that.
to-
but this is Industry 4.0 also,
Who would we look for getting a grant for this?
I guess the state.
We gotta do something. She sent it for 3 years. I think it was $15,000 for 3 years.
Yeah, it's like 5,000, it didn't change any of the amount, it's still 5,000 a year.
I thought it was 6,000 a year. I thought it was. Might be wrong. I'm
I
sorry.
don't know, I thought it was 5,000 a year, but,
You're probably right. The training was 6,000.
yeah, I think that's right.
That's why I got 6,000.
All right, thank you, sorry for the interruption, guys.
So what I have here is so this is a transistor. It's an NPN transistor. And so what we get out of a transistor is we can get a current gain. So my function generator can't put out enough current to run the motor, but I can use the function generator as a reference. Does that make sense? And then I can get a current gain out of the transistor. So what we got is I've got a DC motor right here, a little tiny one, and I have it hooked up to my transistor right here. So this is the motor. This is the power lead coming in to the transistor. So transistors don't create current, they control current. And then this is the lead right here that's coming from my function generator that's turning the transistor off or on. This guy here is rated at about 6 amps, so I could run a pretty good sized motor on that, but that was just the one that I grabbed. So all I'm doing, guys, is I'm just changing the duty cycle. I'm going to change the duty cycle. Of course, first of all, we have to overcome the friction of the motor. I got a piece of tape on it so you can actually see it. And of course, all I'm doing is changing the duty cycle. The camera's not, this camera don't update real fast. I need to put my other camera on here. And I can control it precisely, right? See that? So what I'm doing now is I'm using a pretty small duty cycle. But y'all can hear the motor. Let me increase the duty cycle. You hear the motor speeding up? Of course, that's the best we can do on this. A real pulse width modulation, huh? For this motor, I don't know. We could look up the motor. I think we're getting about a 90% duty cycle out of this thing. So, so right now I'm using this is a 5-volt motor, so I could literally increase the voltage. And that's over 5 volts goes over. So that's all this guy can put out. This is a little 5-volt motor, so it will. Huh? We got a 1 volt per division. That's 1, 2. This is 1, 2, 3, 4. So it's a little less than 4. A little less than 4 volts is all I can get out of this thing. If you came up here and fell this transistor that I'm running with, it's not getting hot at all. If I could do it with a resistor, but when I slowed it down, the resistor would get real hot, right? So what's happening is this transistor is either off or on. So we turn it wide open, and it drops very little voltage, which means it's going to create very little power, right? I square R. And then, of course, when I turn it off, so now the transistor's turned off, and now it's not any power at all, right? You understand? So what's nice about this is we can switch this thing off and on real fast. It still is going to get warm. What happens is it produces power the transistor gets the hottest while it's switching. So the problem we have, I know we need to go loud, is that so when the transistor cuts on, it's going to drop 0 volts, right, or less than 1 volt. And then when the transistor cuts on, the problem is that we can't cut it off and cut it on instantly. So what happens with our current curve, as far as the motor goes, and we'll do this in a different color. So our current would be doing this. So the current is going to be wide open when the transistor's dropping no voltage, and then it's going to go to 0 when it drops it. Well, the problem is your power is going to be maximum right here. So we get a power pulse right there, and we get a big power pulse right there because we got current flow through the transistor, and the transistor's dropping the voltage during that switching time. But what happens is this power is averaged out. I mean, so what happens is you can use very, very small solid-state devices to control, relatively smaller, to control a pretty good deal of current. So yeah, I could control a real big motor on this guy. This guy here has a, if I can find it. Yeah, so this guy right here could dissipate 65 watts of power. So, you know, that's pretty good, right? 65 watts. Without getting into problems. If we get over there, we might burn it up. The biggest problem we have with DC motors is that commutator. Every time it switches, it gives a little spark. And when it gets a little spark, it generates a lot of electromagnetic interference. So I've got another motor up here called a stepping motor. I'm going to show y'all in a minute. And you can see it picking up the noise. See my stepping motor jumping around. So DC motors generate a lot of electromagnetic interference, guys. I mean a lot. On that commutator switching back in the back. So my electronic circuit running this other motor is picking it up. See my stepping motor jerking around over here? So we have a PLC. PLCs are really, really neat. What's the advantage of a PLC, of course, is that it's programmable, which means we can change the program. And it programs in a language that most electricians understand. We call that ladder logic. What you're going to do, though, is if I've got a little task that doesn't require a lot of energy, is you're going to run into a lot of these little guys right here. These are called microcontrollers. This guy right here costs $30. You can get them yourself for $30. But the problem is they program in a language that's very similar to Pascal. So this is the language right here. So this is the program right here. So these are more complicated to learn how to program, but they cost such a little money, right? So I could go out and pay a couple $1,000s for a PLC to run something that I don't need a PLC. So this guy's got outputs on it, just like a PLC. Let me bring my camera up. So all these are output ports over here. Well, that's not true. They're ports. They're programmable. So what that means is you can make any one of them an output port, or you can make any one of them an input port. It's got analog. It's got analog over here. That's what the A's on. It's got analogs on here that I can program, and then of course this is the actual microcontroller right here. But what's nice about this, it's programmable, but it takes a lot more skill to be able to program this thing. But good gracious, $30, right? You understand that? So yeah, you can go to Jamico. This is called an Arduino, which is one of the most popular ones because it's so dang cheap. The programming application is free. Well, when you download it, they'll ask you to make a donation, but you don't have to. So the programming application is free. So you're talking about $39 or $40. I'm sorry, $30, and you got you a program. You got you a controller. You just got to learn a different language, right? So what this is right here, this is a special motor that we call a stepping motor, which we'll talk about next class. And what this thing does is it moves in steps, which is pretty neat. This is a 100-step motor, so that means if I send it 100 steps, it would go exactly one revolution, and then it would stop. Well, the Arduino program I have written is set up so I can just type in a degrees, and then I'll come up here. If I said 360 degrees, what the motor would do is it would turn exactly one revolution, and then it would stop. Sorry. What I need to do is put this up. So this is where I have to enter it, and this is what we're doing. This is where we're watching the motor at right here. So I wrote this program, and that's the actual program there. But I'm going to put this on something we can see it. So I'll try to line it up with a stop, and I'm going to come up here and say 360 degrees. And the motor turns 360 degrees, and then what does it do? Stops. If I say 180 degrees, what should we expect it to do? It'll go halfway and do what? Stop. 180. Okay, so it should come back to the very start. If I come and do 3,600 degrees, guess what it'll do? It'll do 10 revolutions, and then what would it do? It'll stop exactly where I started from. This is called a stepping motor. And you can see what's really neat about these. We can run these things open loop. There's no feedback from it that tells me that it's at 360 degrees. What it does is it's got steps. It's 100 steps. If I tell it to step 100 times, it would go what? It would go 360 degrees. If I tell it to step 50 times, it would go what? It would go 180. Well, all I've done is came up with what we call a transfer function that does a little math that translates degrees into what? Into steps. So if I say 360, the way the program is written is the program is going to send it what? 100 steps. And then we run it through a little circuit right here that takes steps and controls the motor. So this is, all I'm doing is sending pulses in this green wire from our Arduino. It's sending 100 pulses, and then this circuit right here is actually controlling the stepping motor. Neat. So this is what's controlling that carriage over there. The carousel. It's a stepping motor. So it knows to move that thing 45 degrees, it's going to send it so many what? So many steps. So all that thing does is either 45 degrees, which means it stops at the flip and flips it, or it moves at 180 degrees, which brings it over. And then if they turn it 180 degrees, so that's the only two step sizes we have in there. And what it can do